Bismillahirrahmanirrahim. Assalamu alaikum dear student. Welcome you all in lecture 13. In lecture 13 inshallah we will continue the remaining portion of this example. We did a little bit part of this example in lecture 12. So in lecture 12 we basically did this example up to this point. Okay. So you must know that there is a little bit uh, I think this is I want to clear you, okay, this step that from where this 58.1 kip is basically comes out, okay. As we see that they consider the effective depth equals to 20 inches because you know we have I think this 54.6 square, this is the mat here, and this 20 inches is the effective width because we have basically 24 inches overall depth, and keeping 4 inch as a clear concrete cover, so you will get 20 inches, okay, effective depth. So basically here you can see that this 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 distance is considered to be 24 inches, okay, although this distance is taken equals to d, but here they assume that this distance is equal to h, that is 24 inches means 2 foot. So the distance 2 foot are at a distance d, this shear value will be our design shear, okay. This basically you should remember that this 64.6 kip is not our the design shear. We consider VCR is basically our the design shear, okay. So this VCR is lying at a distance of d distance from the face of the support. So how we can determine this? This diagram is not a right angle diagram, okay. There it is. You can say this is 9 kip, okay. This is 9 kip. So you have to distribute this shear diagram into rectangle and triangle, and this value will be round about 9 kip. So the top, this shear area, it will be remain 64 minus 9 gives you this area, okay. 64 minus 9 gives you this shear. Now then you will use, now this point is basically the distance of 10 feet, okay. This lies at the distance of 10 feet, clear. This is at a distance of 10 feet, clear. So now you will use the similar triangular rule, okay. So, and remember that basically, let's see, we will read it, okay. So 64.6 minus 9 divided by this horizontal distance, that is 10 feet. This is similar triangular rule, equals to this VCR minus 9 divided by this distance. Okay, this VCR minus, you should need to subtract this 9, okay. This is constant. So this height, okay, this height is equal to VCR, total VCR minus this portion, and this divided by this distance, clear, this distance, and this distance will be 10 minus 2 gives you. So if you simplify this equation, you can get VCR equals to 58.6, clear. And if you draw it in say, you can see that at a distance 2 feet, how much will be your shear, okay. At a distance 2 feet, okay, at a distance 2 feet, this is 2.0, so 3 kip, this one, this is 58, okay. At a distance 2 feet, if you, this is 2 kip, 58.5, okay. Or if you taking exactly 2 feet, so that will be 58.6, okay. So this is how we can get that 58 value, okay. So a little bit confusion is in this point here. Okay, so I think now it is clear. Okay, and there is also, you know, a kind of uh, confusion. I take this distance equals to 13 feet. So you must know that, you know, in this case the maximum movement diagram will be somewhat like this. Yeah? No, this beam is basically simply supported beam, okay, and it is subjected to UDL plus 2-point loads. Yeah? So how it looks like, you know, the bending moment diagram will be looks like that. Clear? It comes reaches to here and it will 2 degree. Clear? And then it comes 2 degree. Clear? So between these 2 points, although there is a maximum movement that is, you know, a little bit more, because there is a very small difference between these two. So they consider the bending moment constant between these 2 points. Okay, although there is difference, but they consider. So therefore, they determine the value at this point. They taken the distance x is equal to 10 feet. You can take it equals to 13 feet. That don't make any huge changes. Clear? Because the bending moment between these 2 points remain is constant. They they assume that the bending moment between these 2 points is constant. Clear? So you need not to be confused at 13 and 10. Okay, that gives you same result. Clear? Now the maximum moment is achieved. Now you will calculate the AS. So you know mu divided by p. This is the basic formula from where you can get 7.31 square inches, and this is your thickness of your concrete block is 1.43. Again, repeat the process for trial and error method. You will get 5.6.56 square inches. A check confirms that this is well below the maximum permitted reinforcement ratio. 4 number 9 bar plus 4 number 8 bars will be provided. They make some kind of changes because you have to check this area. This A is provided should be less than AS max. Clear? AS max and should be greater than AS minimum. Clear? AS minimum. Clear? So AS max can be achieved from rho max into BD. Okay, and AS minimum you can calculate rho minimum. Okay, rho minimum multiplied by BD, and S provided will be you will calculate. Right? So from these two checks, you know, your this S provided should be large in between. This is the ductility check, and you have to do this check. So this A should be decided 6.56. Okay, 6.56. This is 6.56 square inches. Okay, and it says that it is in between that these two ranges. So this is selected. Now, basically what they did, they provide 4 number 9 bar, okay, plus 4 number 8 bar. Give you exactly this amount of steel. Clear? So basically you see the cross section here. Okay. This is the cross section. Clear? This is the beam cross section. 5-inch thickness, 18 inch is the effective depth, 22 inch is the total overall depth, and you see that 2 number 9 bar. Basically these two are 4 number 9 bar. Clear? 1, 2, 3, 4. This one, okay. This bar, and this bar, and this bar. This is basically 4 number 9 bar. Clear? 4 number 9 bar, and this bar, and as well this bar, and as well this bar. These 4 number 8 bar. Clear? You must know this. Okay, you must know the way they how they place these bars. Okay, and you must remember this is a very important term, that the effective depth should be counted from the center line of these two bars. Clear? From the center line of these two bars, and these bars should be kept at a distance of, the distance of minimum distance should be, this bar, this spacing should be equals to dB. Okay. Should be equals to dB. Clear? So this is all about, the placing of steel. Okay. Now we are this is the design. Clear? This is the design of, this is a flexure design. Clear? Now they did the, I think so, the flexure, the shear design. Okay. So you see that how we calculate these flexure reinforcement and how they place it. Clear? So after that, I think so they will did the shear design. Clear? So let's see. 4 number 8 bar is placed. OK bar at the outer end of the each row. Beam with BW is adequate for this bar arrangement. This bar arrangement, the V is adequate because you must know that these bars are placed in such a manner that it will, uh, it will fulfill the minimum spacing criteria between the bars. Okay, side clear, side cover, and bottom cover, and as well as the clear spacing between the bars criteria should be justified. While the ACI code permits discontinuation of 2/3 of the longitudinal reinforcement for simple spans, in the present case, it is convenient to discontinue only the upper layer. Look, this is the ACI criteria, okay, for simple spans. ACI code says that you can discontinue 2/3 bar. 2/3 bar means if you have 3 bars, you can discontinue 2 bars. Okay. So minimum you have to provide 2 bars. So 2 means if you have 6.56 square inches area multiplied by 2 by third, multiplied with 2 divided by 3, it will give you AST. So that AST you can continue. Okay. If you multiply 6.56 56 multiplied by 2 by third, the value which you can get, let's say the value you can get 4 square inches. So 4 square inches area you should discontinue. Okay, at this point, discontinue, and the rest of the area you will continue. Okay, so this basically this means. But what they say, that it basically, they say that we discontinued only the upper layer at the theoretical cutoff point. Okay, they did basically this process. They discontinue this layer at the theoretical cutoff point. Clear? Basically, this sentence means discontinue only upper layer, okay, of the steel consisted of 1/2 the total area. They discontinues only 1/2 area. Okay, once if you are discontinues 1/2 area, so your area will be 3.57. How it's come, from where it's come? Okay, let's see. Look, you have total area for 6.56. Okay, if you taking its 1/2, it comes out to be 3.56. Clear? So this 3.56 or 7 square inches area is continued and the rest is discontinued. Clear? So now your A will be revised. A will be revised. Okay. So if you, this basically you have to recalculate now your A, because your A will be changed, because your A is changed. From there you can get your add 5 FC prime into B. From there you can get your your A, which comes out to be 0.85, and then you will recalculate your moment capacity. Now if you discontinue your 1/2 bars, what will be your design capacity? Clear? What will be your design capacity? 0.9 AS Fy into d minus a over 2. D minus a over 2. Clear? This is d minus a over 2. So you will get your design capacity will be 300 skep foot. Okay. Now your design capacity gets reduced. Let's see. When you are providing, total sectional area, total AS area, that is 6.56, your moment capacity will be, your moment capacity will be, that is round about more than 510 square inches. Okay. It is not calculated here, but you can calculate your moment capacity from that. Okay. You just put this AS in that equation, you will get your moment capacity, and that will be more than 510 kip foot. Okay. If you are providing your whole AS there, AS Fy into D minus A over 2. We have A value that is 1 point something, AS will be 5.65, Fy is given. So this value, this phi mn value, must be greater than or equal to 510. Okay. So 510, this moment capacity should be greater than 510. Okay. Now as we providing half of this area, our moment capacity will be 300 kip foot. Now this 300 kip foot will be located on the on the moment diagram, and thus we will get the theoretical cutoff point. Okay. So we have a moment diagram from shear. This is our moment diagram. Okay? Now, if this is our moment diagram, so we have to look at 300 point on this diagram. Okay? So, if you look at that 300 point, okay, at what distance it will lies, So you can say that this will be this point. This is 301. Sorry, yes, 301 kip foot. Clear? You have to decrease it a little bit. No, no, no. But so I think so. This is enough. ये जो basically 301 kip foot capacity show हो रहा है. So this 301.83 means it make it 300. Okay. So you will get 5.359 foot. The theoretical point, cutoff point will be from the face of the support up to theoretical point lies at a distance of around about 5.3530 foot from the face of the support. Let's see what that is. Okay, how you can mathematically determine this point? You need to write, your moment equation. Your moment equation is simple. Okay, it is not tricky. You have to select your. Okay, let's say this is your moment diagram, and there is, your 25.6. Clear? So as your cutoff point will be round about in this zone, so you will consider the distance x. Okay, and we make a this reaction is 64.6 kip. So if you write the moment equation, 64.6 multiplied by x minus 3 x squared divided by 2. This is the moment equation for this x. So you need to determine this x value because it is your at this point, your 300 means you compare this mu with 5 mn, and that 5 mn now will be 300. Clear? So 364.6 6 into x square minus 3 into x square divided by 2. Now determine the x value from this equation. The quadratic equation, and solve this equation. You will get round about 5 point something distance. Okay, what did I get basically? Let's see. 5.30. I already told you that it will be round about 5.30. Clear? So your x will be 5.30 from the face of the support. This means that if you draw the moment diagram, okay, your moment diagram looks like this in this shape. Clear? So there is your maximum moment. Clear? This is your maximum moment point. Clear? This is your max moment. So as we consider its half value, okay, this is the half value, that is 300. The maximum is 310. Sorry, 510. Kept put, and this is 300. So we just calculate. We just calculate this point. Okay, this is the theoretical cutoff point, and it lies at a distance of 5.30. So from SAP you can determine it easily. You can also use ACI, which is at the end of this book, ACI tables. Also you can use those tables. Okay, from there you can easily get it. I know, from these tables. Okay, this one. Okay, as you are cutting 50% steel, because 1/2 steel you are cutting, so this point. Okay, this is the point. Okay, this 50% steel is cutting and W is scope. But one thing I mention you, that this chart is basically works out for only UDL, not for fine load. So therefore it fails. You can't use this chart. It only works for UDL. So we are unable to use this chart. Right? Okay. The upper bars must be continued at the least d distance. Now this is the, you can say, the ACI restriction, that as we see that our theoretical cutoff point lies, this is the face of support, and this is your beam. Clear? So this is theoretical cutoff point. Clear? This is your theoretical cutoff point, both sides, from both sides. Now it lies a distance of 5.30, 5.30. Clear? 5.30, and this side also 5.30. Now the ACI provision, this is called shear concentration. You need to continue your, this is the theoretical cutoff point. Yeah? Theoretical cutoff point, TCP. You have to go for your actual cutoff point, and if you are interested to get your actual cutoff point, you need to extend this theoretical cutoff point away from your towards your support, because for positive reinforcement it is towards, and for negative reinforcement it is away. Right? So you need to continue this bar extension towards the support for a distance which is equals to d, or you can say 12 dB, or you may be taken as ln divided by 16, but leaving that one, you can check these two. Okay, so D is, I think so, that is 20 inches. Okay, and your 12 dB is 1.13, and your D is 20 inches, that is 1.504. Sorry, that is 18 inches. 18 inches is given already. This is where is this one? This 18 inches. Okay, so 18 inches is equals to 1.50, and your 12 dB is equals to 1.13. So you have to select the maximum. This one will work out. Okay, clear? So you have to select this criteria. That gives you 1.5 and this 12 dB gives you 1.13. So what you will select? You will select this one. So these are theoretical cutoff point, and this is now actual cutoff point. Yeah, actual cutoff point. So now this is the distance between in these two theoretical points is the theoretical distance of of the whole bars. Okay, theoretical cutoff distance. But now you also need to extend this bar to this side also for a distance of 1.50 because you have to extend in both ways. Okay. So now this is the actual continued length of all of your bars. Okay, they must be continued for a distance of this much. Now what will be now your actual cutoff distance? This will be your cutoff distance. Clear? This one. Your theoretical cutoff distance is 5.30. Now your actual, your actual cutoff distance, your actual cutoff distance right now equals to 5.30 minus 1.50. Yeah, 1.50 because you decrease the theoretical cutoff distance. Now subtract this, you will get your actual cutoff distance, and that comes out to be 3 point something. Okay, 12. They don't get that calculation, but clear cover to the outside. Now it will check out that whether it is development length criteria. Okay, let's say CL. 5.3 minus 1.5, okay, gives you 3.8. So 3.8 is now your actual cutoff point, actual cutoff distance, 3.8 foot. Clear? From the support base. Clear? Now we will checking this distance, whether it is equals to development length or whether it is not equal to development length. Okay, because the bar which is assumed to be cut off at this point, which gives you this is the moment diagram. Okay, and here we assume 300 kip foot. So the bar which is right here, it must be continued for a distance of LD. Okay, because it will support the moment capacity, Mn will be 0, and it will give you 300 capacity when the bar that is 4 bars, 4 half of the LT, when it inserted into the concrete for a distance of LD. So if it inserted or it is embedded into the concrete for a distance of LD, then it will give you 300 foot capacity. Otherwise, if this distance is less than LD, then it couldn't give you that capacity, because the calculation of this 300 capacity we use Fy is equals to 6000 KSI, 60 KSI. Clear? So 60 KSI you can achieve when the bar is embedded into the concrete for a distance of LD. That is the development length. Now we will calculate that development length, because the bars are cut there at a distance of 3.8 foot. Now if this distance 3.8 foot is more than the development length, or it is equals to the development length, then it is okay. If it comes out to be less than the development length, then you can't cut these bars at 3.8. You need to continue the reinforcement. Okay? You cannot cut these bars. Okay? So you will check it. You first of all calculate this development length, and they did that calculation. Here they say For the four upper bars, assuming 1.50 clear cover, as usually we did it, 1.5 is clear cover, and they assume number 3 stirrups at a rate of 10 inches, so it will fulfill the criteria. Uh, the clear side cover will be 1.50, that is 1.88 inches, or you can say 1.66 dB. Means it's 1.6 times of dB. Clear? So you know uh, the spacing in between the bars is clear spacing in between the bars is more than dB. So you are those criteria. I don't want to waste my time in this calculation. I spend a lot of time on this calculation, that how this 1.66 comes out, how this things comes out. You need to recall, revisit your development lecture 7, 8, something like that lectures. So you need to recall those lectures, you will understand. Okay. Assuming equal clear spacing between all four bars, okay, assume it, that clear spacing comes out to be 12 minus 2 multiplied by, now that just find out the clear spacing. How the clear spacing between the bars is determined, okay, you must know how those spacing will be found out, because you must know about the cross section of the beam, that is 12 inches, and there are 4 bars, clear? 4 bars, okay, there are 4 bars, and you must know that this bar and this bar number 9 and this bar and this bar number 8. So how you can get this clear spacing? You must know this calculation, and I did this calculation so much of time in in development lane. You just need to, this is 12 inches, so subtract 12 inches from 12 this side cover, okay, and as well as the bar diameter of bars of 1, multiply 2 with the number 9 and 2 with the number 8 die. Okay, and divide it by 1, 2, 3. You will get the clear spacing. That did it, that calculation. Okay, so this calculation is basically 1.50 is the clear spacing, 0.38 for stirrup, 1.13 for, I think so, that is number 9 bar, 1 is for number 8 bar. Divided by 3, because there are 3 equal spans, 1.3, 1.33, and your clear spacing, your dia bar R, you can say 1.18 dia bar. Okay, 1.18 dia bar. Okay, so 1.18 time, and you have available is 1.66 dia bar. So noting that the ACI code requirements for minimum stirrups are met, it is clear that all restrictions for the use of simplified equations for development length are met. And table 6.1, the required development length. Now they use the development length formula. Okay. So this paragraph is totally, you can say, totally related with your development length lectures. So I don't want to waste my time on these calculations, how these calculations comes out and how 1.1 time. You need to check, those lectures, revisit those lectures, how clear spacing is get and what case it will be. You need to revisit your table number at 1. From there this formula is taken, okay, and psi e factor, psi t factor is 1 1, clear, assume that is 1 1. Okay. So आई थिंक ये चीज़ें आप लोगों को क्लियर होनी चाहिए कि यार हम किस तरह इन चीज़ों को कैलकुलेट करते हैं. डेवलपमेंट लेक्चर में मैंने बेसिकली इसके ऊपर पूरा का पूरा 4-5 घंटे आई विल यूज इट. ओके, आई विल स्पेंड ओके ऑन दोस कैलकुलेशन. सो आपको चाहिए कि आप उनको रिविजिट करें और किस तरह ये स्पेसिंग कैलकुलेट होती है और किस तरह एलडी कैलकुलेट होती है. सो आई डोंट वांट टू वेस्ट माय टाइम इन एलडी. क्लियर? सो योर एलडी कम्स आउट टू बी 53 inches. Clear? And or you can say 4.42 foot. Thus the bar must be continued at least 3 plus 4.4 to 7.42 foot past the midspan point. Now basically they say, what they mean from this, that if you are checking the maximum design criteria, you are interested to check your maximum design criteria. One of the most important principle is that that if you have a simply supported beam, okay, let's say this is okay, this is the beam. Now this is the maximum moment. Clear? This is the maximum moment. So it is necessary that there is the cutoff point. Okay, this is the cutoff point, and this is the cutoff point. The bar 4 number 9 and 4 number 8 bar, which is right here in between these 2 points. Clear? The bars, those 8 number bars, okay, must be continued in between these 2 points for a distance of LD, either to this side as well as either to this side, both sides. Okay. Now LD we calculated that comes out to be 4.42. Okay. So this bar, the total AST which is right here, total 8 bars, they must continue 4.42 feet from the mid span to this side as well as to this side. So if you add, thus the bars must be continued at least 3 plus 4.42. That comes out to be 7.42 foot past the mid span. Okay. Now, but in addition, they must continue to a point 5.30 minus 1.5, that is 3.8 from the support center line. The second requirement controls and the upper layer of the bars will be terminated. Now, you know that the bar will be cut off at a distance of 3.80. These 8 number of bars will be cut off at this point, and similarly from this side 3.80. So the total distance, that it is 26. Okay, good. So how much distance will be these 8 number bars, for how much distance they will be embedded into the concrete, means for how much distance it will be continued from the midspan both sides. Okay? So just subtract 23.8 to 80 plus 3.80 from 26. Okay, 26 minus 3.8 minus 3.8 gives you 18.4. So the bars will be continued in these 2 actual cutoff points for a distance of 18.4, and you required 7 foot, round about 7.4 foot, 42 foot, okay, embedment length, and the bars is right now embedded for 18.4 foot. So your for these 8 bars, your embedment or development length criteria is satisfied right now. Okay, so if the embedment length reduced, okay, to some to some amount of feet, but it should not be less than 7.4. These 8 number bars should be embedded into a concrete both to both sides for a distance of 7.42. Clear? And now I think this criteria is fulfilled. Now we're checking these bars, the 4 bars, whether it is continued for. Now the distance is 3.80. Okay. So if you convert it to inches, to inches, 3.8 multiplied by 12 gives you 45.6. And as well, they are continued 6 inches away from the support as well. So plus 6 inches, gives you 51. Because they are overlap over the support. Okay, the bar is basically 6 inch. The 6 inch extra space is available. So this 6 inches plus 3.8. So gives you total embedment length of 51 inches, and your development length, which is which comes out to be your development length, which is, comes out to be 53 inches. So this is very close. Thus the bars must be continued at least 7.42 foot past the mid-span point. But in addition, they must continue to a point 5.30 is the theoretical cutoff point, minus 1.50 is the 12 dB or dB, okay, 3.80 foot from the support center line. The second requirement controls and the upper layer of the bars will be terminated as shown in figure. 3.30 feet from the support face. Okay, 3.30. The bottom layer of bars will be extended to a point 3 inch from the end of the beam, providing 5.55 feet. How? How it comes out to be 5.55 feet embedment past the critical section of the cutoff bars. Oh, you did a little bit mistake here, right? Okay, because no, you did a little bit mistake. I think so. Look, we have half span is, our half span is, that is 13.5 feet. Okay, I think so. That is 13.5 feet. Okay. Now our that is 13.5 feet. Okay. So what we get? Yes. 1.88. No. 5.30. That is our theoretical cutoff point. Okay. This is our theoretical cutoff point. So subtract this 1.50 from 5.30. I think so. It's give you 3.8. So 3.8. Okay. Now they say that the bottom layer of bars will be extended to a point 3 inch from the end of the beam. Okay, providing 5.55 feet embedment past the critical section for for cutoff of the upper bar. Now, basically, what they did, they count that 5.5 feet from the theoretical point, not from the actual point. So, as theoretical point lies the distance of 5.30. Okay, 5.30. This is what theoretical cutoff point. Right? Now, this is your theoretical cutoff point. This is the bar center line. Okay, and this is the face of the support. Clear? So, you know this this distance is what. Now they say that we should need to continue this lower layer of bar 3 inch inside the support. I think so. Where there I say the bottom layer of bars will be extended to a point 3 inch from the end of the beam, providing end of the beam. Okay, end of the beam. Where is the flare diagram? Okay. You see there. Although they continued it for a distance of 6 inch, they continue it for a distance of 6 inch. Okay, they continue the cutoff. The bottom layer of bars you see here, this dotted line, is continued for a distance of 6 inch, but as well it is continued away from the center line for a distance of 3 inch. I think so. That is this kind of calculation. Okay, so if I add 3.8 plus 0.5, so yes, plus 0.25 comes out to be 4.55 feet. If I multiply it with 10 inches, give me 54.6 inches. And as well, if I have 5.30 plus 0.25, give me 5.55 inches. So basically they did that work. Although they continued it for a distance of 6 inch, but they say here in this sentence basically here this sentence. This sentence is basically means that the bottom layer of bars will be extended to a point 3 inch from the end of the beam, providing 5.55 feet embedment past the critical section of cutoff or upper bar. Okay, you must know one thing, that the 5.30 feet is basically counted from the center line of the support. Okay, these things must be clear. Okay, please give some attention to this point. Yeah. The beam length is measured from the center line. Clear? This is the center line of support. Okay, this is the center line of support. Clear? Now this 5.30 is measured from this distance. Okay, there is you know there is your theoretical cutoff point. This is your theoretical cutoff point. Clear? This is your theoretical cutoff point. Okay, it lies a distance of 5.30, and this distance is basically this distance is basically equals to 6 inches or 0.5. They say in that sentence that this bar should be continued for a distance of 3 inch past the end of them. This is the end of the beam. Okay, here they consider this is the end of the beam. So you need to, although this is the end, okay, this is there the beam ends. Okay, this is the end. But as diagram starts from this point, here this is the start of the diagram. So you need to continue that bar. You need to continue the bottom layer. This is your bottom layer steel. Okay, this is your bottom layer steel. So this bottom layer steel should be continued for a distance of 3 inches. This length is basically 3 inches. Clear? This is 3 inches. So now the total distance, the total cut-up distance for the bottom layer, okay, it comes out from the theoretical point, with reference to the theoretical point, will be equals to 5.3 plus 3 divided by 12 gives you 5.55 feet. Clear? This is how they achieve this 5.5 feet. Okay? This is the embedment past the critical section for cutoff of the upper bars. This 5.5 feet from theoretical point, not from the actual cutoff point. This exceeds the development length of the lower set of bars, confirming that cutoff and extension requirements are met. Okay, as this 5.5 feet is more than the LD. Okay, LD is round about, I think so, 4.42. So as this is exceeding, okay, I already mentioned you that the bars which you are cutting, okay, the bars which you are going to be cut at the theoretical point, okay, there you are, this is your theoretical cutoff point. Now the rest of the bar which you are extending past the theoretical cutoff point is its distance, its continued distance must be greater than or equal to LD. Okay, and as this distance is equal to 5.55 feet, which is more than the LD. So this criteria is much higher, and you can cut these bars and you can continue the rest of the bars here. If this criteria is not fulfilled, either you can provide a hook to the bar, or either you cannot cut the bars. Okay, so or you can even decrease the size of the bar, because once you are decreasing the size of bar, your development length become reduced. They're reduced. Okay, so either you can change the size of bar, you can provide the hook, or you can continue all of the bars. So these are the ACI criteria. You must know these criteria. Okay. Uh, Time is okay. Now I think so. Up to this point, it is clear. Okay. Note that a simpler design using very little extra steel would result from extending all add positive bars into the support. Whether or not the more elaborate calculation and more complicated placements are justified for different clarity. This means that most in simply supported beam designers do not cut the bar. They continue all of bars. Okay, this is a simple calculation because there is a little bit economy. You are just only cutting only 4 bars. Okay, so that because the placement, the cutting of these bars needs some kind of labor cost. So if you don't cut and you continue it, so there is a very little bit economic economy. Okay, so they say that continue overall bars. Okay, don't cut it. Almost designer do it. Okay, but ACI criteria say that you can cut it at the distance of 5.55 feet. Now they're checking that, that kind of check. Okay, as we did in last lecture 11 example. Okay, so as it is a simply supported. Okay, so you need to multiply 1.3, and as this is MN, how? Because we know that the capacity is equals to how much? Capacity is equals to 300 and 300 cap foot. Okay, your Mn. Okay, this is the your. If you draw a tangent with the moment diagram, so this Mn is basically, that is 300 cap foot. 300 cap foot. Clear? So you need to divide this by 0.9. Okay, 0.9. So because 300 is P5 Mn, you need to convert it into Mn. So you need to divide it by 0.9. It gives you 333 kPa. Clear? So you need to multiply it 1.33, 1.3. You need to multiply it and divide by. You need to find out shear, and shear at this point comes out to be 64.6. That is, that is your support shear. Here you must know that you need to take the support shear. Okay, support shear. Okay, that will be something like this. Yeah, this is 64. So divided by 64 plus your LA. Your LA distance is here 6 inches, I think so. That at 3 inches. And right, you must know here. I will mention that explanation. I think so. I give you that explanation. That you there I mentioned this explanation. Okay, this LA is that distance which is providing beyond the point of inflection. Okay, so this extension is basically right here. This is LA. Now you need to recall your lecture number 11, I think so, where I explain these points. That whenever you have a point of inflection means the movement becomes zero. You need to extend the bar for a distance of LA. Okay, and that LA here we extend from the zero movement point up to a distance of 3 inches. So therefore 3 inches added. Okay, so this distance comes out to be how much? It comes out to be 83 inches. And 83 inches is more than LD. That is 53 inches. LD is 53 inches. So your this criteria is also met. Clear? The actual LD is 53 inches and meets this criteria also. So you check this criteria also. You check the LD criteria whether development length is fulfilled or not fulfilled. And now, since the cut bars are located in the tension zone, special binding stirrups will be used to control cracking. These will be selected after the normal shear reinforcement has been determined. Okay, now you have to check. I left this topic. And uh, I will say that I will do in numerical because at this time you are not able to understand these three criteria. Okay. So this topic, that whenever you are cutting your flexure bars in a tension zone, so there is a shear stress concentration, and they're causing, they become the cause of the development of shear cracks. And once those cracks are developed at that cutoff points, due to which there is a huge concentration, huge transfer of tension to the to the discontinued bars. Okay, if you okay, see, I will explain it a little bit, although I will explain in so many lectures in so many times. Okay, so for example, this is a beam, clear. This is a beam, you know, and you have you have bottom layer, and you cut off the top layer, clear. So this cutoff point, right at this cutoff point, right at this cutoff point, there is shear stress concentration. Okay, there, and there, due to this shear concentration, cracks develops, clear. And those cracks, basically what they did, due to this kind of cracking, the whole tension is transferred to this flexure bars, these bottom layers. Okay, and at this moment the whole tension is taken by this lower bottom bars. So due to that, there is a there is a lot of chances of the failure, okay, at this section. So therefore, that this kind of, to control these kind of cracks, we use three criteria, and those criteria are right in front of me. Okay, right in front of me. Criteria number one, that at this point 2/3 your developed shear, which is developed at that point, must be less than, okay, that shear must be less than 2/3 of the total shear strength of the concrete plus shear strength of the uh, stirrups. And similarly, the next criteria is that we will check at that criteria. Okay, we will check at that criteria that the spacing of the stirrups should be minimum. Okay, and the stirrup period should be greater than. So you need to use only one criteria. One criteria must be specified. Okay, so basically they use these two criteria and they ignore this criteria. One criteria must be fulfilled. Let's see. Let's see. They calculate, first of all, what it should be noted, that whenever you are cutting your bars in tension zone, not in negative tension zone, okay, negative steel area. This calculation is only carried out for positive reinforcement only, not for negative reinforcement. Okay, because it is a tension zone, and the cutting of bars in a tension zones, it give birth to shear stress concentration. Okay, so ACI do not permit you to cut the bars in tension zone until these three in these three criteria, one criteria should be met. Okay, so first of all, they calculate the shear strength of the concrete, that is 5VC 0.75. That is a well-known criteria formula for which find out the shear strength of the concrete. Okay, that is 20.5 kip. Okay, now the web reinforcement must be provided for that part of the shear diagram shown shaded. Now, number 3 stirrups, okay, will be selected. The maximum spacing must not exceed d/2. Okay, now that design shear reinforcement. Okay, you have to design shear reinforcement. They say that because I already mentioned you in lecture 10, lecture 9, that how these shear design is carried out. So you must know about shear design. At this moment, this is my not responsibility to define your shear design. Okay, you must know about the shear design. So these 5 or 4 criteria are used for shear design. From these 4 to 5 shear criteria, we will determine the spacing. Okay, spacing of stirrups. So you see that This is a design spacing criteria. Okay, this is a design spacing criteria that gives you 4.04 inches because you have 64 and 20 is the shear capacity and 64 is the maximum shear. So 4.4 inches is the controlling criteria. Okay, so that did basically this through this way that basically did the uh, design of shear. Okay, so the spacing selection of spacing is that this. Okay, this is the minimum criteria from where they determine the spacing of stirrups, and this is the final design. Okay, first first stirrup will be provided at a distance of 2 inch from the face of the support. Okay, then they select 4 inch center to center. 7 stirrups are placed for a distance of 28 inches. So total distance is 30 inches. Then they select 8 spaces at a distance of 5 inch and they cover 40 inches. And then they select 5 spaces at a rate of 9 inches, they cover 45. A total of 115 inches is covered, 9 feet 7 inches from the face of the support. That gives you 121 inches, 10 feet 1 inches from the support center line. If you see your beam, okay, that's fine. Okay, first stirrup is placed at a distance of uh, here. Here you see that this small distance is equals to 2 inches. Sorry. First stirrup is placed at a distance of 2 inches from the face of the support. Then they select 7 stirrups at a rate of 4 inches center to center. This much. Okay. Then they select 8 stirrups at a rate of 5 inches center to center. And then they select 5 stirrups at a rate of 9 inches center to center. Okay. Now, after that, no stirrups are required. So basically, you know that this 3 foot 4 inches, which is I think so, and 1 point, this is used stirrups. Now, let's see. This is your cutoff point. This is your cutoff point. This point. This is your cutoff point. 3. The bars are cut there. Okay. The bars are cut there. This is your actual cutoff point. Okay. Now, at this cutoff point, they determine the shear, and at this point, they determine the minimum shear area. Okay. So let's see. Okay. Now, to number 3, longitudinal bars will be added to meet anchorage requirements and fix the top of the stirrups. Okay, they provide number 3 stirrup, number 3 bars. Okay, at the top. This means here these 2 bars are number 3. Okay, because they are provided there, for the to suspend the stirrups from this. Okay, because they act like a confinement bar. Okay, so stirrups are suspended from these 2 bars. So they are provided just only for suspension purpose. Number 3 bars, 2 number. Okay, this basically means that. Anchorage requirements and fix the top stirrups at their own place. In addition to the shear reinforcement just specified, it is necessary to provide extra web reinforcement over a distance equal to 3 by 4 of D. That is 13.5 inch from the cut ends of the discontinued steel. Clear? Basically, this means that whenever you are cutting bars, here they cut the bar. Okay, this is the actual cutoff point. Once you cut the bar, you need to provide some extra stirrup here for a distance of how much? For a distance of 3 by 4 into D. This is the ACI criteria. Okay, this is the ACI criteria. You need to provide extra stirrup from the cutoff bar okay, from the cutoff bar towards the tension zone for a distance of 3 by 4d. Now, what will be the spacing of those extra bars? They will be determined. Okay, let's see. The spacing of these extra reinforcement will be d divided by add beta b. You know, add beta b. So what is d? D is the effective depth, that is 18 inch. Add is constant, and 1 over 2 is what? You know. Let's see. Comes here. Well, beta b is the ratio of the area of the bars that are cut up to the area of the bars immediately before the cutoff. The bars which is cut up and the bars which is immediately before the cutoff. Okay, means 3.57 is continued, and I think so 6.56. Okay, so let's see, check it. 3.57 divided by 6.56, I think so, gives me 0.45. They're taking it as 0.5. Okay, so this beta b is a kind of ratio. Okay, it is a ratio of the cutoff bars, okay, to the continued bar. Yeah, from there. Okay, the minimum spacing of the extra stirrup is S is equal to d divided by add beta b, where beta b is the ratio of the area of the bars that are cut off to the area of the bars immediately before the cutoff. I think so. Yes. The area of the stirrups AB is not to be less than, and this is another check. Okay, you have to provide the bars for a distance of 0.7475 d or 3 by 4 of d. 3 divided by 4 comes out to be 0.7. Okay, so this 0.7 means 3 by 4 of d. So you have to extend the bars from the cutoff point for a distance of this much, and your spacing must be equals to this much, and you are providing area of stirrup AB. You are providing AB. It must not be less than this much. 0.60 BWS divided by FYD, and they will be checked. Okay, this one. Okay, 0.054 inches. 60 BW is 12. S is S is a 4.5 inch. Let's give you 4.5 inch. This spacing. This S is basically this one, and divided by 60,000 give you 0.054 inches. Then you are providing number 3 stirrups, and number 3 stirrups AB is equals to 0.22 square inches, because you know that number 3 stirrup area in stirrups, that is 0. So 0.22 is more than 0.054. So this check is also okay. So for convenience of number 3 stirrups will be used for the purpose also, providing an area of 0.22 square inches, which is more than that one. The placement of the 4 extra stirrups is shown in. Now, how much extra stirrup is required? 4.5 inch their spacing for a distance of 13 points. So divide 13.5 divided by 4.5 gives you 3, means 4 number of bars will be extra will be used behind the cutoff point. Okay, and you will see here, okay, this is the cutoff point, and I think so this is the cutoff point, and for a distance of 1 foot 1 sahi 2 inches. Okay, 1 over 2 inches. So this comes out to be 13.5 inches. For 13.5 inches towards this point, you have to provide 4 extra bars at a rate of 4.5 in center to center, and this is the ACI criteria. Okay, so here this design is, I think so, completed. It is a very interesting calculation, and it is very very interesting calculation. Okay, and this is your complete design. Okay, design of TV. Okay, you use this criteria. Okay, here. So this criteria must be fulfilled. Inshallah, in Greater book, you will see you will fulfill this criteria. Okay, so this topic is also clear. Okay, and you will understand that how we did the how we can get the actual cutoff point. Okay, the actual cutoff point is and the theoretical cutoff point, how we extend theoretical cutoff point to the actual cutoff point. Okay, so basically we see that calculation, but remember, most of time designers that don't did this calculation, they continue this tree in the case of simply supporting beam, because if you continue these trees towards the support, you don't need to do this all up calculation, which we did okay, which we did for which from beyond this point. Okay, you don't need this calculation if you continue that stage. So it is a time consuming process, you know, and although you did this calculation, okay, for sure you have to do that calculation, but this calculation and the last calculation you will see, you don't do this calculation. So it is a, you know, it and then providing these extra stirrups, so designer don't want to waste their time, and because the placing of these extra stirrups, they need some labor force also as well. So they say that there is a little bit uh, economical uh, cost variation, so they say that continue this bar throughout the line. Okay, so in simply supported beam, you can calculate these bars. Okay, that don't make any great changes. Okay, so I think this is the end. If you have any doubt about this topic, although it is a tricky, and my time is also so much extend from my 1 hour. So if you have any question, I welcome. Okay, I give my address also as well. And any doubts, you can ask questions about this topic. Okay. So up to this, I think inshallah we will continue this topic for further examples, and they are more tricky and more explanatory than this example. Okay. So inshallah, see you in lecture 14. Thank you.